It is my pleasure now to introduce our next speaker, Sui Tang. The title of her talk is Operator Estimation in Dynamical Sampling. Yes, please.
Okay, thanks. So good morning, everyone, and thanks for the organizer for the invitation. And it's a pleasure to be here. Today, I would like to discuss a research problem in the intersection of sampling theory and dynamic system, operator estimation in dynamic sampling. It is about how to reconstruct a dynamic system from its observations. Okay, so this line of research is motivated by the pioneer work of Martin Vitali and Yue Lu and many others on wireless signal networks, and they found many engineering applications. And then Akram Ajoubi, Ilya Crystal, and Jackie Davis actually formulate these questions into a unified and abstract setup, now what we call the dynamic sampling problem. I have been fortunate to work with a brilliant team on dynamic sampling problem. And this talk is based on the joint work with my previous student, Jiahui Chen, together with Christian Cumirio and Mauro Maggiani, based on two papers. And the first one is on how to estimate the eigenvalue of a fine dynamic system from partial observations of a single trajectory data. And the second one is a more recent advancement, like how to recover the full transition operators in a dynamic system from partial observations of multiple trajectory data. So these two papers serve as our roadmap in the dynamic system journey. Okay, now I will begin with more detailed introduction and motivation to this kind of problem. So in a typical sampling and reconstruction problem, and we typically ask how to reconstruct a function, what we call a signal of interest from its samples, say fxj. And the classical sampling theorem, like the channel sampling theorem, tells us the criteria when we are safe. So the samples has to be dense enough in order to recover f. However, in modern applications such as like sensor networks and neuron activity monitoring or transport flow problems, and this kind of like signal of interest is often undersampled. We simply because we simply don't have enough many sensors to record the samples. So in this kind of scenario, reconstructing F become like ear post. And this actually leads to the core concept in dynamic sampling. As we are actually in the dynamic scenario and all the signals are evolving over time, so we want to sampling the evolving signal ft and model the equals to some operator AT acting on f at various times and ask the question, so when do the coarse sampling taken at various time contain the same information as the final sampling taken at the earliest time? So here, the tricky thing is that at every time instance, and this omega t is very coarse, so it's actually we cannot let the samples satisfy the liquid density criteria, and we want to leverage the anion physics and to still achieve the recovery of the function. So in other words, we are looking for a space-time trade-off. Okay, below I show a formulation of abstract dynamic sampling problem, work for both finite dimensional and infinite dimensional setup. And suppose this mu t is a physical quantity we are of our interest, and it is satisfied the following dynamic system. And here A is called a transition operator, and it is defined, for example, in its domain. And this says this mu t lies in a helpless space H. And this F models various type of source and external forces. And there are two types of dynamic sampling problems. The first one is that suppose we know the governing equations, so A is known, for example, and we take samples of these physical quantities, like say at a space-time grid xi ti, and we would like to solve this initial value problem from these space-time samples. On the second scenario is more challenging than the first one. We even don't know the underlying Governing equations, and we want to recover this dynamic system from the observations. Our research goals are threefold, and for the theory level, we want to characterize the space-time samples for identifiability. And for the algorithm levels, we want to turn the space-time samples into the estimators of dynamic system. In particular, we would like to develop a mathematical framework to do error analysis. So this can inform us how to find space-time samples to optimize the recovery. And this is very relevant to the sensor placement problem in engineering applications. So I would like to remark that in the case of time-space trade-off problem here, where A is known, we already have many results available to characterize the identifiability. Actually, this problem is deeply connected to the frame theory. So in our scenario, we are interested in when the dynamic system acting on a set of sampling vectors can generate a frame for the helpless space edge. This is a very in similar spirit with wavelets, where people use the scaling operator and translation operator to generate a less frame for the whole space. And while in our scenario, we have a dynamic system. And compared to the theory side, for the first category of the problem, actually the algorithm side is underexplored, is in particular for the system identification setup. And this is going to be the focus of today's talk. Okay, so let's focus on this problem in a specific setup. And together with my student during the COVID, we began to look at this problem. Suppose now we have a finite dimensional dynamic system like xt plus 1 equals to axt plus c, and say this x0 equals to some vector b. So now we are looking at a finite dimensional space like this single nodes of interest xt, say is a vector in Rm. And so this discretized system can be viewed as a discretization of the previous continuous time on uniform uniform in time observations. Okay, so in this scenario, we denote omega t by the sampling time, by the sampling locations. So this is a subset of the indices from 1 to n. And we denote the sampling operator by S omega t. So this acting on xt means we observe the entries of xt corresponding to the indices in omega t. So in this way, we collect a set of observations and we ask, can we recover something from these observations? When we formulate this problem, we found out it is a generalization of a very classical harmonic retrieval problem in the signal processing or applied harmonic analysis literature, where people are interested in recover the signal is a complex value signal of this form. So it consists of the M exponential sum, and the people are interested in recovering this Cj and Aj called frequency from the measurements corresponding to x0, x1, x2. So it's kind of evaluation of this signal on the integers. If we actually introduce the operator A acting on this signal x by shifting it on the time domain, and then the measurements is exactly a single trajectory generated by dynamic system, and recovering this frequency is equivalent to recover the spectrum of A. So inspired by this previous line of the work, we think in our generalized setup, we also should consider eigenvalue estimation of the affine dynamic system. Then why eigenvalue estimation is relevant? Because this dynamic system has applications to model a variety of dynamic phenomena, and the eigenvalue, for example, can tell us the mixing rate of random walks, and the efficiency of diffusion process, and the stability of dynamic system. In particular, if this dynamic system is defined on graph, and then the eigenvalue of A can tell us the underlying graph topology. So this is one of the central topics in spectral graph theory. So we want to know how to recover them. And then to find the idea, we look at this harmonic retrieval problem again. Actually, this problem is solved by a very elegant algebraic method called pruning methods. And it now has 200 years old history. And then we generalize actually this idea to deal with a affine dynamic system. And the idea is summarized in this slide. And in this figure, we showcase how this algorithm work. So here we have a 7-dimensional dynamic system. And so here each column represents some xt's. And in this example, we take the sampling set omega t all the same through the time axis. So here we choose 1, 2, 4, and 6. So you can see we have 4 colored lines in this dynamic system. And given these observations, we arrange it in a particular way to form a Hankel-like matrix. And through this Hankel matrix, and we can form a matrix system. And by solving this matrix system, we get a coefficient vector which can form the analytic polynomial of the operator A. And then from this analytic polynomial, the roots, we can find some eigenvalues of the operator A. So in this way, we recover eigenvalues. But then the central question is that given this sampling set omega, which eigenvalues can be recovered and which cannot? In other words, we want to find a relationship between the sampling location and the observability of the eigenvalues for the A. And we want to say in what way they are dependent on the spectral properties of A. Okay, so we are able to develop various categorizations, and below we showcase one of such results, which we concern so-called universal sampling set. So we say omega here, so like this 1, 2, 4, and 6 is called a universal sampling set if we can recover all eigenvalues of A for almost every initial state. And in this theorem, we develop 3 equivalent conditions. We show this sampling problem is deeply related to the frame theory question. So equivalently, we require the set of vectors generated by the joint operator of A acting on the sampling vector EI for I in omega. So this EI is a canonical basis vector in the space CD, can generate the whole space CD. So in other words, we have the summation of the Krylov subspace generated by A star acting on ER will equals to a full space. So in the third condition, we develop a characterization for arbitrary matrix A, leverage their Jordan decomposition. So given J is a Jordan block for A, we actually introduce a Penzelhaus family for this operator J. And it consists of the PS. The PS is orthogonal projection from the space CD onto the spine of cyclic vectors corresponding to the near-point block. And if this PS U star EI for I in omega can span the range of the PS for every near-point blocks, and then the condition 2 is true, and therefore omega is universal sampling set. So why the third condition is useful in practice? Because in many scenarios, the range of PS is low dimensional, typically is 1 or 2. So by checking this condition locally, it's actually easier for us to design universal sampling set omega. And I also want to point out this theorem is for linear dynamic system where we assume C equals 0. But we are able to generalize the result to cover any affine linear system and with arbitrary matrix A and based on the Jordan decomposition of A. And for the algorithm side, we can definitely do pruning methods for recovery. However, pruning method is well known to be actually noise intolerance. So in the singular processing literature, people have developed its stabilized version called the matrix pencil and the ISQGD method. And we're able to adapt those ideas also to cover this general dynamic system setup. But we also want to make 2 comments. And first of all, this kind of algebraic method is intrinsically sensitive to noise. because we want to recover the roots of some polynomial. Think about if the coefficients of polynomial got perturbed, and of course the roots maybe also will got perturbed quite a lot. So this is a kind of, and from this, we can also say this problem become challenging if the eigenvalues are close. So it's very hard to, so this kind of like two challenges are kind of essential in this kind of algebraic method. And also by our theory, we found out in the case of single trajectory data, eigenvalue estimation should be our optimal goal because it's really, really challenging to recover the full transition operator. In fact, we show that if one can recover the operator from a single trajectory data, then this kind of operator A can generate a frame by only choosing the one of this kind of omega. So basically, if we apply the iterated action of A on single sampling vector, it should generate a frame. But we can see that such operator A is very restrictive in structure, so we cannot expect it's true for every operator. This actually leads to us to the second phase of research. How about we have access to multiple trajectory data? Then can I recover the full transition operator? And here is kind of our formulation. Suppose now we have the same dynamic system, but we are able to simulate the dynamic system using different initial conditions. Here for simplicity, we say the initial state are the canonical basis vector Ej, localized for all j in N. So in this setup, we are able to see the action of the transition operator on the full space. So mathematically, let's simplify the problem a little bit. And we consider like entry-wise observation to these actions of the transition operator. Let's say we have entry-wise observation of the matrix power a squared, a to the cube to a to the power t. Can I recover this operator A? Below, I provide an example to illustrate this sampling scheme. So in this figure, in this top panel, and we plot the entries from A to the 7. We use the colors to represent the values of the entries magnitude. Below, we showcase how we observe these matrix powers. So here, these colored ones are the locations we observe the entry. And while the white ones are the locations that are not observed. By collecting these samples, we want to recover A. Now, let me mathematically formulate this problem. We denote a sampling set omega now is a union of the samples we collect at a different time instance. So here in this matrix setup, this omega t here will be a subset of the matrix indices like n times n. And we introduce a monomial map Qt and mapping our transition operator A into the observation space. Now it is a direct sum of matrix powers, analyzed in the direct sum of matrix space. And then we introduce a sampling operator P omega. So this is a classical in literature. P omega is a linear operator. It acting on our observation space. So it is an operator from the direct sum of matrix space into R omega. So here we have a typo. There should be cardinality of omega. So this formulation actually characterizes the sampling scheme we presented here. Now the problem is that given Y, can I recover A? And this inverse problem is challenging for two reasons. The first of all, if you look at this sampling operator, is a composition P omega, a linear one with a nonlinear one. And this matrix powers making the relationship between Y and A quite complicated. So it's kind of more challenging than the linear inverse problem. The second reason is that we kind of get ambitious to set the bar that we want to recover A even when A is full rank. So why when A is full rank is a difficult problem. To say the difficulty, let's make a comparison. If we say the t to 1, then the problem essentially asks the question when we can recover a matrix from its partial observations. So this is a well-known matrix completion problem. By the work of Candace and al., we know that if the observed entries are random and A is incoherent, so I will explain the incoherence later. Then there are results saying that if the number of observed entries satisfy this inequality, well, C is a constant dependent on incoherence property of the matrix A, and N is the ambient dimension of the matrix, and R is the rank of the matrix. And then with high probability, one can recover A by convex optimization techniques. So in this scenario, this Rn log n can be viewed as a Nyquist density theorem for a rank R matrix. And now let me explain what incoherence means for a matrix A. So basically, this is a geometric quantity measures how information is scattered around the entries of A. And we want to avoid the case like A like identity matrix. And this is a matrix with high incoherence parameter because if you observe the diagonals, which are all ones, it's very hard for us to infer other locations are zero, right? Because 0 and 1 has a large gap. However, if A is a constant matrix 1, so all entries are 1, and this is a matrix example that A has a low incoherence. So in this scenario, if you observe any entries like of A, like say 1, you are able to recover the other entries. Okay, so back to our case. In the dynamic sampling, we are interested in the case where T is bigger than 1. So we ask, like, can we recover A from possibly higher rank, like even this R equal to N, from measurements of multiple time instance? Well, at each time instance, this omega T is small. And here, this Rn now is the Nyquist sample density for the matrix A to the T because the rank is still R. And by collecting these samples at a multiple time instance, you will say the total sampling set M is still like greater than their Nyquist sample density. Can we still recover A? Okay, so we consider two sampling regimes. So this is to align with the literature in matrix completion. The first one is we assume the observation is independent uniformly at random without replacement. The second one, which we call like adaptive sampling, we assign a probability to each space-time location, and we assume the observations like follows a Bernoulli distribution. And due to time constraint, I will only present the result for the first sampling regime, which we call the uniform at random sampling. Okay, recall that this is a nonlinear inverse problem. And then our idea is to overcome the nonlinearity is to linearize the problem. So how to linearize the problem? We introduce the operator H. So this is a block-Hankel embedding operator. It maps from the direct sum of matrices into a structured matrix space RD1n times D2n, where D1 is the height of the matrix and D2 is the width of the matrix. So you can see that suppose x tilde equals to x1 plus x2 direct sum xt, we arrange these blocks in a structured way that it actually form a Hankel structure. Our conjecture is that if we have dynamic system data, they are all in the dimension Rn times n. Now we embed them into a higher dimension space, which is D1n times D2n. This D1 and D2 will be dependent on our sampling time. And then this should still to be a low dimensional object in this high dimensional space. So here this low dimensionality is measured by the rankness. So we conjecture this should be still a low rank matrix in this high in this high dimension space. So we want to actually solve this problem by a rank minimization problem. So this is currently a hypothesis. And below we show one of the theorem actually saying this hypothesis is true. So in this theorem, we say that if we replace this x tilde here by our monomial map QTA, so this is a direct sum of matrix powers, and we'll make this a block Hankel embedding, then no matter how large T is, the rank of H still equals to the rank of A. Even A is full rank, say A is N, now this H lies in the space Rn D1 times N D2. When D1, D2 are large, so N is still considered as small in this larger matrix space. So our rank minimization becomes valid. And here in the second part of the theorem is kind of messy, but essentially we want to prove a converse side of the part one. And here we show this is no rank. Then we ask if any no rank block Hankel matrix can be realized by some matrix powers. So we're able to characterize some particular cases for it, but this is too messy, and so I will skip it. Now, our previous theorem saying that we can translate this recovery problem to a rank minimization problem, like we show here, by leverage the low rankness of the block Hankel matrix. And then the problem still remains because from matrix completion literature, we see that this optimization problem is actually non-convex and also NP hard to solve. There are already many literature on how to relax this optimization problem. And here we adopt an approach called iterative reweighting square algorithm. It actually find a appropriate surrogate function for this rank by a smooth one, and then solve this problem while solving a sequence of least square problem. And then the difficulty lies how to tune a parameter epsilon such that the iterative process of this algorithm will give us the ground truth solution. And this problem is non-convex. And this kind of algorithm generalized the idea initially proposed by Dobeshiz, DeVoe, and Flanzier, Ganterk, and Rahat and Watt for the sparse recovery problem. And more recently, my collaborator generalized this line of algorithm to cover matrix completion. So in our work, we generalize this algorithm to cover the block Hankel matrix. Okay, so in the following theorem, we are able to provide theoretical guarantees for the previous algorithm. So this is kind of informal like theory statement. We say if this block Hankel matrix is mu0 incoherent, and the number of random measurements m satisfy the inequality below, then with high probability, the previous algorithm will converge quadratically to the ground truth and recover A, provide we have a good initialization. So let me make several remarks to understand the theorem. And first of all, we will look at this inequality, the constant here. We found out if we choose D1, the D2 equals T over 2, and then this will make this quantity independent of T and also small. This actually corresponds to our observation in numerical examples that when we make this block Hankel matrix like a square matrix, and the estimator will perform better than other choices like a rectangular shape. And somehow from this constant, we can get some partial observations, a partial explanation to that phenomena. And also this incoherence parameter, as I mentioned before, it was defined for the matrix A, and now we generalize this notion to define with the block Hankel matrix, and it is closely related to mu0A. In particular, for many cases, we're able to get a closed formula like how does this incoherence parameter dependent on mu0A. And for example, when A is orthogonal matrix, and we can show this incoherence is smaller than or equal to 1, this is actually an optimal scenario in matrix completion. In this setup, and then we know the n squared log nt space-time samples is enough to recover A, no matter how large T is. So later I will provide an example to illustrate this. And also if A is positive semi-definite, this happens when A is a diffusion operator, for example. And this, we can show that this incoherence is bounded by the ratio of mu0A and the smallest positive eigenvalue of A. And about Rn times log nt space-time samples will suffice. And Last, let me comment also the computation complexity about this algorithm. And so you can see that recovering a full rank matrix is always harder because this sampling density is higher than the low rank matrix, and also for the computation cost per iteration if R equal to N. So you can see it's more expensive. And okay, so now let me showcase the algorithm.
Your time is almost gone.
Okay, then sorry for that. So yeah, I will actually skip for this experiments. So here I want to comment our current work is about finite dimensional, and the infinite dimensional case is generally open, and we would like to investigate for future work. And thanks for your attention.
Thank you. Is there any question just for 30 seconds or something? If not, let us thank the speaker again. Our next talk will start after 1 minute.